Molar mass. Well, we often need to know how many atoms are in a sample. And the reason we need to know numbers of particles is because chemical processes happen between particles. They don't happen based on mass, they happen based on numbers of particles. If you form water as H2O, which reminds me of a joke an old lady at the nursing home told me yesterday. So if water is H2O, what is H2O for? Drinking? What is H2O for? FOR? Little white-haired old lady in a wheelchair told me this joke. I'm like, this is so awesome. Anyway, H2O, 2 hydrogens, 1 oxygen. Always, always, always. And so when hydrogen and oxygen react with each other, it's the numbers of particles that tell us how they're combining. The masses are useful because that's how we can measure them. But we need this relationship between mass and numbers of particles. So when we want to know the numbers of atoms in anything that's like big enough to see, we count them by weighing. And we often use counting units for large quantities. So we're very familiar with a dozen. How many donuts are in a dozen donuts? 12. How many eggs are in a dozen eggs? 12. How many blocks are in a dozen blocks? 12. A dozen means 12 things, right? A gross of objects, have you heard of that unit? That's gross. A gross is a dozen. 12 times 12 is 144. So a gross of little glass sampling vials, there's 144 of them in the box. Just a number of things. Well, those units are nice, but those numbers are way too small for what we need. So we have what we call the chemist's dozen, and it's called the mole, M-O-L-E. So it's not a sauce, and it's not a little short-sighted animal that burrows under the ground. It's mole. It's abbreviated MOL, which I think is really silly because the word itself is so short. Why does dropping the E make any difference? Molecule is a long word that does not have an abbreviation. But this is how it is. So mole is abbreviated MOL. So if you see MOL, it's exactly the same thing. A mole is an amount of material that has a particular number of particles in it. Like a dozen is 12 things, a mole is this number of things. 6.02214 times 10 to the 23rd particles. That's a 6 with 23 zeros after it. We can't even begin to realize how huge that number is. That number is called Avogadro's number, after a scientist named Amadeo Avogadro. And now I have to tell you about my son Michael. So you've heard of Pi Day, right? 3.14, right? So March 14th, the mathematicians celebrate Pi Day. And then May the 4th, Star Wars, May the 4th be with you, right? Well, scientists have Mole Day. Mole Day is October 23rd. 10/23. 10 to the 23rd. So celebrated between 6:02 a.m. and 6:02 p.m. So I'm a chemist, my husband's a chemist. Our 4th child was born on Mole Day. And he weighed 10 pounds and he was 23.5 inches long. So 10/23 on 10/23. We missed the 6:02 thing, but you know, we decided to keep him anyway. We had a discussion that lasted, maybe 10 seconds. Should we give him Avogadro as a middle name? No, we're not going to do that. So we didn't do that. His name is Michael. Anyway, so he's my mole baby. 1 mole of anything is this number of pieces. Just like you could have a dozen donuts or a dozen cars, you can have a mole of pennies. They wouldn't fit on the planet, but you could. You can have a mole of atoms, a mole of ions, a mole of molecules. It's just a counting number. Now, hopefully you've all heard of the mole and Avogadro's number before, but maybe it didn't quite make sense to you. So hopefully the second time around, you'll go, oh, okay, I see what that is now. This number is the number of atoms in a quantity of stuff that is reasonable to deal with. So 22 copper pennies are going to have approximately 1 mole of copper atoms. You know, you can hold those in your hand. A tablespoon of water is approximately 1 mole, Avogadro's number, 6.022 times 10 to the 23rd water molecules. So a mole of substance is a reasonable quantity to deal with. Any questions? Where did the number come from? That's a good question. So remember we talked about how the atomic mass unit was defined as 1/12 the mass of a carbon-12 atom. The value of the mole ties into that as well. The value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. So 12 grams of carbon-12 is equal to 1 mole of carbon-12 atoms, which is 6.022 times 10 to the 23rd carbon atoms. You should memorize this number. We usually leave the 1,4 off because 4 sig figs is enough, but we do know it further out for more precise things. This gives us a relationship between number of carbon atoms and mass. So now we can weigh out a sample of carbon and calculate how many atoms are going to be in that sample. It's a little bit like going to the hardware store and buying nails. You know, if you need, 2,500 nails for a fence, you're not going to stand there and count them out in the bin. You're going to look at the sign on the bin and it's going to say, there's 15 nails in a quarter pound or something, and you'll weigh them to get the correct amount. So we can convert between moles and numbers of atoms, just like we can convert between dozens of eggs and numbers of eggs. For atoms, we're going to use this conversion factor. A mole of atoms is equal to this many atoms. So, if I tell you, I went to Costco and I bought 5 dozen eggs. We actually did. How many eggs? 60. How did you do that? Multiply by 12, right? So what you're doing in your head, which you can do because it makes sense to you, 5 dozen eggs, well, there are 12 eggs per dozen. Right? The dozens cancel out and you get 60 eggs. It's the very same idea with a number different than 12. It's a weird number. So these are the 2 variations of the conversion factor. Moles over 6.022 times 10 to the 23rd atoms, or you can upside down it. So let's do a problem. A pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver atoms does it contain? So this is the equivalent of saying I've got 60 eggs. How many dozen eggs is this? So we write down the number that we're given. 2.80 times 10 to the 22 atoms. Okay, it's a number of atoms. And the question is, how many moles? So this is a unit conversion, a dimensional analysis problem. We're going from atoms to moles. The relationship is Avogadro's number. 2.80 times 10 to the 22nd atoms times, and we want moles on the top and atoms on the bottom. And then we have to put Avogadro's number in the correct place. Well, just like it's 1 dozen is 12 eggs, mole is the chemist's dozen. So 1 goes with mole, and Avogadro's number goes with atoms. Then make sure that the scientific notation is working on your calculator. 2.8 EE 22 divided by 6.022 EE 23. How many sig figs should this number have?
3.
It should have 3. Our starting number of atoms has 3 sig figs, and Avogadro's number, as we've written here, has 4. Avogadro's number is not an exact number. So I've got 0.0464. There's my third one, and then I'm just going to write down 2 extras. That many moles. And then I'm going to round it 0.0465 moles. Remember, those leading zeros are not significant figures. Did I get the answer right? Yeah? If you came up with a number that's like crazy huge, you're having an issue with scientific notation, please come talk to me in lab and I will straighten your calculator out. It's your calculator's problem. Any questions?
Yeah, I have one. So this is my calculator just sets the scientific notation, so it gives me the answer in scientific notation. Is that okay?
It's okay, yeah. So if it gives you your answer in scientific notation, 4.65 times 10 to the minus 2.
Yeah.
In my opinion, writing a number in scientific notation is never wrong, unless the question is asking you to say, here's scientific notation, write it in decimal. That would be the only time. Any other time, you can write it in scientific notation. Kind of a guideline is, well, when should I? My guideline is, if I can't immediately identify how many zeros are involved, I want to put it in scientific notation. I always feel like a kindergartner when I have to get my finger or a pencil out and count zeros, right? So this is just 0.0, that's fine. We could leave it, or we could put it in scientific notation.
Will mastering chemistry mark us wrong if we do it in scientific notation?
I don't think mastering chemistry will mark you wrong if you do it in scientific notation. I don't think so.
It requires
Sometimes it does require it, yeah. Mastering chemistry is a little pickier than I am about some things. But it's a machine. What do you expect? Not very good at being flexible. Any other questions? So we talked about counting atoms by weighing them. We still haven't done that yet. We need one more conversion factor, and that would be the mass of 1 mole of atoms. That is called the molar mass. So think about this. The atomic mass is the mass of an atom. The molar mass is the mass of a mole of atoms. So the molar mass is the mass of a mole of atoms. And this is the beauty of how they chose Avogadro's number. An element's molar mass in grams per mole is numerically the same as its atomic mass in atomic mass units. So 26.98 grams of aluminum is 1 mole of aluminum. That's going to be Avogadro's number of aluminum atoms. The average mass of 1 aluminum atom is 26.98 atomic mass units. That's equal to 1 aluminum atom. So on the periodic table, I told you that the number below the element symbol was the atomic mass in atomic mass units. It is also the molar mass in grams. Okay, so it does double duty. Any questions? If we look at this little illustration here, aluminum atoms are larger and heavier than carbon atoms. And so when we're talking about a mole of aluminum atoms or a mole of carbon atoms, it's the same number of atoms, but the masses are different. Aluminum atoms weigh more, and so if you have the same number of them, the total's going to be more, right? If you have a dozen ping pong balls and a dozen bowling balls, are the masses going to be the same? No, because bowling balls are like 10 pounds each and ping pong balls are almost nothing. So mole is a number of things, and then how much that dozen, that mole of things weighs, depends on how much each of the individual things weighs. So the molar mass of any element is a conversion factor between the mass in grams of that element and the amount in moles. So for carbon, 12.01 grams of carbon is equal to 1 mole. So we can make 2 different conversion factors out of that. Okay. Now, on the periodic table on the wall, on periodic tables that you might find other places, you'll see that the number of significant figures varies a little bit. They do update the periodic table occasionally as new information is discovered or new measurements are made, and so they fine-tune it. The periodic table on the wall here has oftentimes 6 significant figures for the atomic masses. What I'm going to be using in class is basically 4 sig figs for each element. Partly because I've memorized a lot of them that way, partly because in the problems that we're doing, it's very unusual to need more than 4 significant figures. And so putting on all those extra numbers doesn't really benefit anything. If you want to use all the digits on whatever periodic table you are referring to, that is probably the best thing to do. Just use whichever periodic table you're presented with, just use all the digits that are given there. So let's calculate the amount of copper in moles in a 35.8 gram sheet of pure copper. So these are dimensional analysis problems. We are given 35.8 grams of copper. And we want to know the number of moles of copper. Well, do we have a relationship, or can we find one, between grams and moles? Yeah, it's on the periodic table. So look on the periodic table, and under carbon, 63.55. So 63.55 grams of copper per 1 mole of copper. So that tells me I can go from grams directly to moles. 35.8 grams of copper. I have 1 conversion factor. I'm going to have moles on the top and grams on the bottom because I want those units to cancel out. I look at the relationship. The 63.55 is with the grams, and that's 1 mole. Molar mass is the mass of 1 mole. So the units tell us that we're dividing. 35.8 divided by 63.55. I get a whole mess of digits here. I'm going to keep 2 extras. So I should have 3 sig figs. So 0.563, and then I'm going to write down 2 more. And that would, the unit would be moles. And then I'm going to round it for my final answer, 0.563 moles of copper. Any questions? This is like one of the most important types of calculations we do in chemistry. We convert grams to moles all the time. Because when we look at chemical equations, we're concerned about moles, numbers of particles, but to measure things, we often use grams. So now we have everything we need to actually count atoms by weighing them. And the way this would be done, you get the mass of a sample, you convert the mass in moles. We convert the mass to moles, okay, yeah, grams to moles, using the element's molar mass, and then we convert the number of moles to number of atoms. So grams to moles to number of atoms. Conversion factor here is the molar mass. Conversion factor here is Avogadro's number. So how many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure copper. Carbon. Diamonds are made out of carbon. I knew that. And we're told that a carat is 0.20 grams. Okay, so this is a little more involved because they're throwing this extra unit in there, a carat. Which makes me think of rabbits. Okay, so we're starting with 1.3 carats. So So that's the number provided. This is a conversion factor. I would not expect you to know that, but it's just given to us. And what are we trying to find? How many atoms? So we're looking for carbon atoms. So now we have to figure out how to get from carets to atoms. I should probably have written that over a little further.